Okay, so get this. Using radio waves to see through walls. That's what we're diving into today.
Sounds interesting.
We've got this research paper from MIT, their Computer Science and AI Lab, CAOL. It's called This AI Senses Humans Through Walls.
Yeah, I saw that one.
And it's not just, detecting that someone's there. It actually creates like a skeletal outline, a 2D pose of a person behind a wall.
Really challenges what we think is possible, like with sensing technology.
Totally. So how does it work? I mean, I know radio waves can pass through objects, but how do you go from that to actually seeing a pose?
Well, they developed this system called RF pose, and it takes advantage of the fact that the human body reflects radio waves.
Wait, so we're like walking radio mirrors?
Kinda, yeah. And depending on our pose, our bodies reflect those waves differently. So RF pose picks up on those variations in the reflections and uses that to figure out, like, put together a person's posture.
Okay, I think I'm following. But it can't be that easy, right? Radio waves aren't exactly known for their high resolution. It seems like you just end up with a blurry picture.
That's true, and that was a big challenge for them to work through. So that's where machine learning comes in. They use something called a teacher-student network.
Now we're getting to the good stuff.
Yeah. So imagine you've got a really skilled artist. That's our teacher network. And this teacher already knows how to draw the human form perfectly from regular images.
Okay, so the teacher knows poses from like visual data.
Right. And then the student network, that's our RF pose, is learning to predict poses, but from radio signals. Like, it's almost like trying to learn Braille by studying regular print.
Yeah.
The researchers basically kind of tricked the AI into understanding radio waves by showing it images.
That's a really interesting way to think about it. So they're basically teaching this student AI to translate between two totally different types of data.
Exactly.
And the results are impressive.
Oh, yeah.
Well, don't leave me hanging. How does RF pose actually perform compared to those, traditional vision-based systems?
Well, they compared RF pose with open pose, which is a state-of-the-art vision-based system. And for situations where you can actually see the person, RF pose is nearly as accurate as open pose.
Wow. That's pretty amazing when you consider it's basically working with like a much blurrier image of the world.
Right. But here's the really interesting part. When you start talking about walls, RF pose really shines. It achieved over 58% average precision in through-wall scenarios.
So that's like over half the time it's getting the pose right, even through a wall.
Yep. And meanwhile, the vision-based system, open pose, just completely fails because it can't see through the wall.
Okay, now this is starting to feel like something out of a sci-fi movie.
Yeah, it really is pushing the boundaries. But it's important to remember, like any technology, RF pose has its limitations.
Right. So let's dive into those. What are some of the things that RF pose has trouble with?
Well, one of the biggest things is the low resolution of those RF signals. That does affect its accuracy. It's better at picking up larger body parts, like the head and torso, things that are moving a little slower.
Because those are easier to like pick up even with the blurry signal.
Exactly. It's like if you're trying to track a ship on a radar screen versus a speedboat, the ship, like our torso, it's easy to spot. But those smaller, faster things like limbs, they're a little tougher to pin down.
So it's a trade-off between size and speed and the resolution of the data.
Exactly. But there are some other interesting kind of nuances too, like RF pose is less prone to false alarms than a vision-based system.
False alarms, what do you mean by that?
Like think of a poster of a person on a wall. A vision-based system might actually think that that's a real person, but RF pose can tell the difference because it's sensing the reflections, not just light and shadow.
So it's less likely to be fooled by like visual tricks.
Right. But on the other hand, because of that low resolution, sometimes RF pose struggles with the precise location. So it can tell there's an elbow, but the exact pixel perfect location is harder to get.
And of course, we can't forget about metal objects.
Yeah. Metal blocks RF signals, so if someone is behind a, metal door or a cabinet, RF pose won't be able to see them.
So it's not completely foolproof.
It has some weaknesses, but the potential here is still amazing.
Yeah, totally mind-blowing.
And they actually didn't stop at just figuring out the poses. They trained another AI to analyze how those RF-based skeletons move, to see if they could actually identify people.
Wait, are you saying they can tell who you are just from how your skeleton moves, like through a wall?
That's exactly what they did.
Yeah.
They had 100 people walk around, and they were able to identify individuals with over 83% accuracy.
That's wild. So it's like a fingerprint, but for movement.
Exactly. Like you and I might walk in a similar way, but there are tiny differences in our gaits that RF Pose might be able to pick up on.
This is really making me rethink what's possible with AI. It's not just about, like, crunching numbers. It's about finding really creative ways to understand the world around us.
It really shows you the power of machine learning to connect things
Mhm.
that, you might not have considered before.
So I think we've covered a lot here. From RF reflections to teacher-student AI networks, we have a pretty good understanding of how this RF pose system works.
Yeah, we've laid the groundwork.
But the big question is, what can we actually do with this technology? That's where things get really exciting. We'll explore some of the potential applications and implications of this mind-blowing research after a quick break.
It's funny when you think about it.
What's that?
This whole thing really hinges on something as basic as reflection.
Right. It's like we're seeing, I don't know, like seeing the world through a new lens. Or a new wave, should I say.
Exactly. And the paper actually goes into, more detail about how these RF signals behave, especially compared to light. They talk about this concept of RF specularity.
Okay, that sounds a little intimidating. Break that down for me.
Okay, so remember how we were saying that our bodies are like mirrors for radio waves? Well, the paper explains that this mirroring happens because the wavelength of RF signals is actually bigger than all those, like, tiny bumps and imperfections on our skin.
So basically, to these radio waves, our bodies are basically smooth.
Exactly. And that has this interesting consequence.
I bet it has something to do with, like, how the radio waves bounce off us.
You got it. So the angle that the signal hits the body, it actually really matters. It determines, like, whether the signal reflects back to that RF sensor or gets, deflected away. So imagine someone standing with their arms at their sides. The signal's probably going to bounce right back from their torso, giving RF Pose a pretty clear view.
But if they turn sideways, then, like, suddenly their arms could disappear from the RF image.
Exactly. It's almost like a game of hide and seek with these radio waves. And that's why just using, like, one snapshot of RF data wouldn't work. For accurate pose estimation,
Ah, I see what you're saying. If you only looked at one frame, you might miss entire limbs just because they happen to be, like, positioned in a way that deflects the signal.
exactly. That's one of the big insights from the paper. RF Pose needs to analyze how those reflections change over time. So by looking at a bunch of frames in a row, it can build a much more complete and accurate picture of the pose, even if some parts are hidden, for a moment or two.
I get it. It's like those flip books, where each page has a slightly different image, and then you flip through them, and it creates that illusion of motion.
That's a perfect analogy. RF Pose basically stitches together all those snapshots of RF data, like the frames in the flipbook, and that creates a moving image of the person's skeleton.
The whole thing is just, I don't know, so clever. It's pretty amazing how much thought went into designing this.
Yeah, it really is. And they had to solve all these problems, like, without any labeled data. They couldn't just, feed the system images of people with their poses all nicely labeled.
That's right. They had to get creative. They used that, what was it called, like a cross-modal supervision approach or something, where the AI is learning from multiple different types of input.
Exactly. That's one of the coolest parts. They basically tricked the system into learning how to understand those radio waves by showing it images at the same time.
So the visual data is like a translator, kind of like a Rosetta Stone, helping the system to decode the radio signals.
Yeah, you put it that way. This deep dive is really showing us what machine learning can do. It's not just about processing data. It's about finding new ways to teach machines how to see the world.
Absolutely. So we've talked about how RF Propose works, but now I'm curious about the data they use to train and test this thing. Like, what did they actually look at in the real world?
They really went all out. They collected over 50 hours of data from, like, all kinds of different places on the MIT campus.
Yep.
And not just, labs.
Yeah.
They wanted to see how it would do in, like, real world settings.
So something more challenging than a controlled lab.
Yeah. They gathered data in, like, offices, cafeterias, classrooms, even hallways and stairwells. Talk about a diverse set of environments.
Wow. So RF Pose had to learn to deal with all kinds of different contexts. And did they have people doing specific things or just, going about their day?
Mostly just everyday stuff. Walking, talking, sitting, working, even waiting for the elevator.
So RF Pose had to figure out all sorts of different postures.
Yeah, exactly. They even had some people jogging to test how well the system handled faster movement. And then, to really push it to the limit, they built this whole setup to test its through-wall capabilities.
Okay, tell me more about that through-wall testing.
They basically created this mobile system with 8 cameras.
Yeah.
to capture really detailed 3D pose data, even when the person was completely blocked by a wall.
8 cameras. That's
It
serious.
was quite the setup. Basically, they used those cameras to create a really accurate 3D model of the person's pose, even though, the person was completely hidden from the RF sensor.
So even though the RF sensor couldn't actually see the person, they had this other system that was providing like the ground truth. So they could compare and see how RF pose was doing.
Exactly. This way, they could really rigorously evaluate RF pose's output, see how well it matched up with the actual pose, even when hidden behind a wall.
That's a really smart way to test it. And it's even more impressive, like you said earlier, that RF pose wasn't specifically trained on any through-wall data.
Right. It figured it out on its own. Basically, it learned everything it knows about through-wall pose estimation from the data where the person was visible.
So it's like it took what it learned in one context and was able to apply it to a totally different situation.
That's the beauty of generalization in machine learning. And it really speaks to, like, the potential of this technology.
This is really incredible stuff. It makes you wonder what else we might be able to see with technology like this.
Absolutely. And it brings up all sorts of questions
Uh-huh.
about privacy and security and even, like, how we think about personal space.
Exactly. So we've talked about how it works, the data they used, but I'm curious about, its limitations. Are there situations where RF pose might not be as reliable?
That's a great point. Like any technology, it has its weaknesses. There are definitely situations where it might not perform as well.
Well, let's talk about those. What are some of the potential pitfalls? Things to watch out for. So some things that can trip up RF pose.
Well, like we've been talking about, the low resolution of those RF signals, that's a big one.
Yeah, it's like trying to paint a really detailed portrait, but you only have like a giant brush. You can get the shapes, but not the fine details.
Exactly. So RF pose is great at detecting a person and kind of their general pose, but the exact spot, like where each joint is, that gets a little tricky.
Especially those smaller joints, I imagine, like fingers or toes.
Right.
So no RF-powered hand tracking for our VR games just yet.
Not quite. But, I mean, this is still really early research. Who knows what the future holds?
That's true. Technology is always changing. But for now, sticking with what we know, what other challenges did they run into?
One thing they found was that, how accurate the system is, it can be affected by how many people are around.
That makes sense. I mean, if there are like a bunch of people close together, their RF reflections are going to overlap, right?
Yeah. It's harder for RFOs to separate those out.
Yeah.
Who's who.
Like trying to follow one conversation in a really crowded room.
Exactly. More noise, harder to pick out the signal you need.
And speaking of noise, are there any environmental things that can mess with RF pose?
Well, we talked about metal objects.
Yeah, the RF kryptonite.
But other things can get in the way too. Thick concrete walls or a lot of water, even some types of furniture. It can all distort the signal.
So RF pose's vision isn't completely clear.
Not always, no. The real world's tricky like that. But even with those limitations, what they achieved, especially with identifying people by how they walk, it's remarkable.
That was the part that really blew my mind. Like, they can tell who you are just by your walk, even through a wall.
Yeah, it's wild. It's like, we all have those little unique ways we move, fingerprints for our skeletons almost.
Yeah.
It's amazing that RF Pose can pick up on that, even with limited data.
Makes you wonder what other, like, hidden signals and patterns are out there,
Yeah.
just waiting to be discovered.
That's science, right? Pushing the boundaries into the unknown.
So we've reached the end of our deep dive. What are the key things you think people should remember from all this?
Well, first off, this research, it really shows how RF sensing could change how we, see and interact with the world. It's not just about, like, the see-through walls thing. It's about all these new possibilities for understanding how people behave, for safety and security, maybe even, for games and entertainment.
Like a sixth sense almost.
Yeah, kind of. And then also, this research shows how powerful machine learning can be. To learn from all sorts of data, even stuff that seems weird, it's really creative how they got RF Pose to recognize people from radio waves.
It's a good reminder that, like, we're only limited by our imaginations.
Exactly. And I think, lastly, this work raises a lot of questions, ethical questions, that we really need to think about as this technology keeps developing.
It's not enough to just ask, like, can we do this? We need to think about how will this be used?
Right, because technology, it's a tool. It's up to us to use it responsibly.
So, listener, as you go about your day, maybe you'll look at things a little differently. Remember, there's a lot more to our world than, what we see with our eyes or even what the RF sensor sees.
There's always something new to discover, something to learn, and something to question.
Thanks for joining us for this deep dive into the amazing world of RF sensing.
Yeah.
Until next time.